Hello and welcome back. In the previous lectures, we're talking about fugacity. We looked at the need for using fugacity in phase equilibrium calculations. We said that at phase equilibrium, just like chemical potentials of a species in each of the phases is equal, the fugacity also will be equal. We related it to the Gibbs free energy or the residual Gibbs free energy. We also defined fugacity coefficient as the ratio of fugacity to pressure or partial pressure in case of mixtures. And we said that as the limit P approaches 0, the fugacity coefficient will approach unity and the fugacity itself will approach the pressure. We looked at how to use various equations of state to calculate fugacity in case of pure species. We have used the virial equation of state. We have also used a cubic equation of state to calculate fugacity and even the Lee-Kessler tables for fugacity coefficients. In case of mixtures, we defined what is known as Fi hat, the fugacity of species I in the mixture, or phi hat, the fugacity coefficient for species I in the mixture, and related it to the partial molar Gibbs free energy, the residual partial molar Gibbs free energy Gi bar R. In case of the mixture, we said as the zero pressure limit, the fugacity will approach the partial pressure of that particular species. To be able to calculate fugacity of mixture species in a mixture using virial equation of state, we said that we need what is known as a mixing rule to be able to calculate the virial coefficient B for the mixture. It is related to the individual virial coefficients B11, B22, the mole fraction Y1, as well as an additional virial coefficient B12, which we called as the cross virial coefficient. And once we have the information about these virial coefficients, we can use the relations shown here to calculate the fugacity of the species in the mixture. We can also extend this formula to multi-component mixtures. Now, what we have shown here is for a binary mixture. Now, pure virial coefficients and the cross virial coefficient can be obtained from experiments or from the theory of corresponding states, for example, using correlations such as these for B0 and B1, which are related to the reduced temperature. And once we have B0 and B1, I can calculate B Ij. If I equals j, then we have the pure species second virial coefficient. If I is not equal to j, then we have what is known as the cross virial coefficient. And to be able to calculate Bij, the cross virial coefficient, we can use what are known as the combining rules to obtain the pseudo critical constants or the pseudo critical parameters, such as Tc12, omega12, the compressibility factor, the volume, etc., from which we calculate the pressure. And once we have this information, I can calculate the cross virial coefficient B12. We have used this in an experiment and calculated the fugacity coefficient for species in a mixture. What we will do today is look at how to calculate fugacity coefficient of a species in a mixture using cubic equation of state. If you recall, we have used a variety of cubic equations of state, the van der Waals, Redlich-Kwong, or Peng-Robinson, Swayam, Redlich-Kwong, etc. Each one of them can be written in a generic form as shown here, with several parameters A, B, etc. listed in there. In case of SRK and Peng-Robinson, we have an additional parameter alpha, which will give a functionality to the parameter A in terms of the temperature or the reduced temperature, and the eccentric factor omega. Now, we have used this cubic equation of state successfully to calculate the fugacity of pure species, but for a mixture, what we need is, just like in case of virial equation of state, I need mixing rules, right? I need mixing rules to be able to apply these cubic equations of state as well for a mixture. The mixing rules we are going to use are what is known as a linear mixing rule for B. I'm going to write B indicating it is a parameter for the mixture, it is related to the individual pure species mixing rules via this equation xi bi, sigma of xi bi. So for a binary, it reduces to B is x1 b1 plus x2 b2. Similarly, the parameter A, we use a quadratic mixing rule, ij xi xj aij, and for a binary this reduces to x1 squared a11 plus 2x1 x2 a12 plus x2 squared a22. As usual, a11 and a22 are the A's for pure species 1 and 2, and a12 is the cross parameter, and for this particular scenario we will get it via a combining rule, and the combining rule we use to get a12 is square root of a11 times a22, right? Once we have a11, a22 and a12 from the combining rule, I can apply it if I know the mole fraction in the mixing rule and get the A for the mixture. So these are the mixing rules we will use for a cubic equation of state, right? Once I have this information, I can work through the math to obtain the partial molar Gibbs free energy Gi bar by RT, which in turn is related to the fugacity coefficient of species I in the mixture ln phi I hat. We won't go through the math, but we will write the final expression. It turns out to be Bi over B z minus 1 minus ln z minus beta minus qi bar O times I. And qi bar here is given as the derivative of nq with respect to ni at pt and nj, and this in turn boils down to q times 1 plus ai bar over a minus bi by b. And finally, ai bar again is the partial molar A, so we will write it as derivative of n times A over Ni at P, T, and Nj. For a binary, this simplifies to A1 bar is 2x1 A1 plus 2x2 A12 minus A2 bar is 2x2 A2 plus 2x1 A12 minus A. Because of the definition we have used, note that A12 is going to be equal to A21. Both of them are square root of A11, A22, right? So with this, what we have, if you look at the formula from the previous slide, I have an expression for ln of the fugacity coefficient phi I hat. It is given in terms of Bi, which is B for species I, over B, which is B for the mixture. Maybe I should write that here to bring more clarity. This is for species I, this is for the mixture. If I don't have any subscript, it's for the mixture. If I have a subscript, it's for that particular species. Then this is also for the mixture. This is also for the mixture. And if you recall, beta was B times P over RT. If you look at this here, beta is B times P over RT. So I use B for the mixture times P over RT. That will give me beta. That beta is for the mixture. I, again, is given by these two definitions here. I have Z, which is for the mixture, beta for the mixture, and sigma and epsilon come from the equation of state I choose. And finally, Qi bar times Qi bar is given by the expression here, which in turn has A and B. The partial molar A and B for the mixture, Bi is for the species I, and the partial molar A itself is given by the definition here, and we can reduce it in terms of A1s and A12s for a binary mixture, right? So once I have this information, I should be able to calculate the fugacity of species I in the mixture. Things will be a little clear if we start working with one example and see how we can calculate each of the quantities we need. So let's work on a problem. Let's say I have a mixture of ethylene, let's call this as 1, plus propylene, let's call this as 2, at a temperature of 373 Kelvin, the pressure is 30 bar, and the mole fraction Y1 is 0.4. These are the conditions given to me, and I'm interested in calculating phi1 hat, phi2 hat, the fugacity of species 1 and coefficients for species 1 and 2, as well as the fugacities for the species 1 and 2 in the mixture using, let's say, Peng-Robinson equation of state. We have not used this equation of state so far. Let's use that in this particular example. This is what I want to calculate. To do this calculation, we'll run through a series of steps and follow the procedure given to us. So what I'll do is I will list some quantities for species 1, for species 2, if there is any cross coefficient for 1, 2, and finally for the mixture. All right, let's start working with some of these quantities. The first one I will try to get from a handbook is Tc, the critical temperature. For ethylene it is 282.3, for propylene it is 365.6. We don't need it for 1, 2 or the mixture. Pc is 50.4, this is in bar, this is in Kelvin of course, and for 2 it is 46.65 bar. I don't need these using an equation of state. We got 1, 2, PC12 or TC12 when we used ideal equation of state, the pseudo-critical parameters. For cubic equation of state, we don't need those numbers. Then the eccentric factor omega is 0.087 and 0.14. Using this TC, I can get TR as 1.321 and 1.02. I can get PR as 0.595 and 0.643. In addition, I can get B. If you look at this equation, B is omega R Tc over Pc. I have Tc, I have Pc. I can use a value for R, and omega for Peng-Robinson equation of state is this number here. So that is B I need to calculate. So let's write that equation here. It is omega R Tc over Pc. That is what I'm trying to calculate. I have Tc, Pc, and in appropriate units, I should be using R as 83.14 bar Cc per mole Kelvin. When I do that, the value of B I will get is 36.23 for 1, 50.69 for 2. There is no 1, 2, but for the mixture, I will use the combining rule x1 b1 plus x2 b2, right? So this value here is going to be 44.91. Well, I should say, because this is a vapor mixture, I'm going to, let's say, call it as y1 b1 plus y2 b2. We don't know if it is a vapor or a liquid mixture. Then we can use x1 to be the mole fraction in a more general sense, but it really doesn't matter as long as we stick to the same notation. So once I have B, the next thing I would like to calculate is A. If you go back and look at our table, A is given by this expression here, which requires psi alpha r squared Tc squared over Pc. So we run through this calculation. The first thing I will calculate is alpha for Peng-Robinson equation of state, which is this number here, right? It needs omega and the reduced temperature. Once I have the reduced temperature and omega, I can calculate alpha. I will plug that alpha in here. The psi for Peng-Robinson is given here. And I get psi, I get alpha from the equation here, and r squared Tc squared over Pc, everything else is known. So once I finish that calculation, this is the number I have for A. Again, I'm working with a R of in bar Cc per mole per Kelvin, and the value of A I get for 1 is 4269046. B is 8949250. A12 is square root of A11, A22. That number turns out to be 618100. Well, 618100, 3 zeros there. And for the mixture, it is a quadratic mixing rule. This value turns out to be 6871657. A is x1 squared A11, or rather, since we're using y's here, it's y1 squared A11, y2 squared A22 plus 2y1 y2 A12. That's the equation I have used to get A for the mixture. Right. So these are the numbers I have for A and B. Notice the units for B in this case are going to be same as that of the volume. So B is going to be in Cc per mole, and A is going to be bar mole square centimeter to the power -6. These are the units for A. So with these numbers, I can go to the next step in my calculation, which is calculating the partial molar values for A1 bar and A2 bar. A1 bar, if you recall, is 2x1 A1 plus 2x2 A12 minus A. In this case, I have all the numbers I need, so I can calculate this numerical value to be this much. And similarly, A2 bar is going to be 88122242. Once I have A1 bar and A2 bar, I can calculate Q, right? 1 bar, it is Q times 1 plus A1 bar by A minus B1 by B. So this value here turns out to be 3.7977. And similarly, Q2 bar is Q 1 plus A2 bar over A minus B2 by B, which works out to be 5.6924. The other thing I need in these calculations is beta, which is BP over RT. We already have B for the mixture from the previous slide. The value we had was 44.91. The pressure here is 30 bar. R is 83.14 times 373. This value works out to be 0.043444 beta. Once I have all of this, if you look at the equation we have here for ln phi hat, I have Bi B beta Q1 bar and Q2 bar, of course. What I don't have is I and the value for Z, or the compressibility factor. And if you recall, I also is related to Z. So I think the next step to in this calculation is to find the value of Z at the given conditions. To find the value of Z, the compressibility factor at the given temperature and pressure, if you recall, what we need to do is solve the cubic equation. We get and obtain the roots of that cubic equation. The cubic equation in this case, right, let's show that cubic equation once for sake of, well, we don't have it here. So that cubic equation in this case works out to be Z cube minus 0.9566 Z square plus 0.1218 Z minus 0.00734 equals 0. And the roots of this cubic, there is only one real root. The other two are imaginary. The real root works out to be 0.8187. That's the compressibility factor at the given conditions, temperature and pressure conditions, right? Using the values of A for the mixture. This is for the mixture. So when I get the coefficients for this cubic equation, I have used A and B for the mixture, and then once I get the coefficients, I can find the root to be that. So this is for the mixture. Let's highlight that. So once I have Z for the mixture, I can go back and calculate I, which is 1 by sigma minus epsilon ln of Z plus sigma times beta, Z plus epsilon times beta. For Peng-Robinson, sigma is 1 plus square root of 2, epsilon is 1 minus square root of 2. I have the value of Z, I have the value of beta, so I can plug all those numbers in to get a value for I, which turns out to be 0.05047 in this case. Now once I have I and Z, I have everything I need to calculate the Fugacity coefficient. Ln phi1 hat now turns out to be 0.0834. So phi1 hat is going to be exponential of that value, 0.834, which is 0.92, and f1 hat is going to be phi1 hat times the partial pressure y1p, which is 11.04 bar. And ln phi2 hat for propylene is 2374. Phi2 hat is 0.7887, and F2 hat works out to be 14.2 bar. So this is how we use a cubic equation of state to calculate the Fugacity coefficient and Fugacity of species in a binary mixture. Of course, we can extend this to a multi-component mixture. So what we have done so far is demonstrated the need for Fugacity and tried to calculate Fugacity using a variety of approaches, virial equation of state, the Lee-Kessler tables. We have used a cubic equation of state both for mixtures as well as pure species. There is one other interesting way to calculate Fugacity for liquids or condensed phases, right? Now if you recall, when we calculate Fugacity using virial equation of state, it is mostly applicable only to vapors until moderate pressures. If I'm going to use a cubic equation of state to calculate Fugacity, of course I can, if at the given conditions the equation of state yields a liquid-like root, then I can use that equation of state to calculate the Fugacity of the liquid. So we have a scenario now where I can use virial equation of state to calculate Fugacity of a gas or a vapor, but that is applicable only up till moderate pressures. The only approach that probably will work for calculating Fugacity of a liquid in whatever we have looked at so far is using a cubic equation of state. If I have a cubic equation of state and that yields me a liquid-like root, then I can use it to calculate the Fugacity of the liquid. I can use the liquid-like root for the compressibility factor Z and extend whatever calculations we have done so far to calculate the Fugacity of the liquid. But then for that approach to work, the equation of state needs to be applicable over the entire range of pressures from zero pressure to the pressure of our interest. If it is not sufficient, if the cubic equation of state only works for the pressure we are looking at, it should work for the entire range, because the equation we have obtained is actually via an integration from zero pressure to the pressure P of interest, right? So unless we are able to find such an equation of state which is applicable over the entire range of pressures, we will not end up with a correct value for Fugacity or Fugacity coefficient using a cubic equation of state. The other way to calculate Fugacity of a liquid, we are talking about pure liquids here. So what we do is we use the concept of vapor liquid equilibrium to calculate the Fugacity of pure liquid. Let's say I'm interested in Fugacity of liquid at a certain temperature and pressure P. This is pure liquid, so it depends only on the fugacity will depend only on temperature and pressure. Let's call this as liquid, right? This is what I'm interested in calculating. Now, this fugacity of liquid, let's give a subscript I so that we're talking about species I, although it is pure component, will be related to the Gibbs free energy of the liquid, Gi liquid, via this equation, some constant plus RT ln Fi. And at the saturation condition, at this temperature T, let the vapor pressure be Pi sat for this liquid. At the saturation condition, that is Gi sat, which is at T and Pi sat, right? At this condition of T and Pi sat, let's say the Gibbs free energy is Gi sat. At this condition, because the temperature is same, the constant is still going to be same, plus RT ln Fi sat. Now, if I subtract one from the other, then it turns out that Gi liquid minus Gi sat is RT ln Fi liquid over Fi sat. So what this means is that the fugacity of liquid at a temperature T and pressure P will be Gi liquid minus Gi sat over RT, exponential of this multiplied with Fi sat, right? So the fugacity of liquid at any temperature T and pressure P will be related to the fugacity at temperature T and pressure Pi sat via this equation. Now, there is two things I want to add on top of this equation. The first thing is at vapor liquid equilibrium, recall that the chemical potentials, the Gibbs free energies, and hence the fugacities of the pure species are going to be equal, right? And we're talking about vapor pressure Pi sat. So at T and Pi sat, the vapor and liquid are in equilibrium, and the fugacities at this condition are going to be same. So I'm simply going to call this fugacity value as Fi sat, right? It doesn't matter whether I'm talking about the liquid phase or the vapor phase. The fugacity is same. We are simply going to call it as the fugacity of saturated vapor or saturated liquid. We'll simply say Fi sat, right? This Fi sat will be related to the fugacity coefficient at this condition Phi sat times the vapor pressure Pi sat, right? And it is easy to calculate the vapor phase fugacity, like we have seen. We can use a second virial coefficient, we can use cubic equation of state, whatever it is at the saturation condition to calculate Phi sat. The simplest way, of course, is to use the virial equation of state, let's say. So I can calculate the fugacity at the saturation condition using virial equation of state. And so the previous equation, Fi liquid, will be exponential of Gi minus Gi at the saturation condition over RT, right, times Phi sat times Pi sat. Now let's see what I can do with this equation, Gi minus Gi sat. Recall that dGi is Vi dP as long as the temperature is constant. I can integrate this from Pi sat to P. This will be integral of Pi sat to P Vi dP. I'm integrating it over the liquid phase from the saturation condition to the pressure P of interest, right? When I do this, on the left hand side I have Gi minus Gi sat. On the right hand side it is integral of Pi sat to P V dP. So what I can do is I can replace this thing here in terms of Gibbs free energies with the integral of V dP or Vi dP. So essentially that equation now boils down to Fi liquid is going to be exponential of integral Pi sat to P Vi dP over RT times Phi sat times Pi sat. The vapor pressure multiplied with the fugacity coefficient at the saturation condition multiplied with the exponential term in here. For most liquids, over moderate changes in pressure from Pi sat to P, Vi is fairly constant. So I can take that out of the integral sign there, in which case this equation will reduce to exponential of Vi liquid times integral of dP will be P, so that definite integral will be P minus Pi sat over RT, exponential of this term. This is a fair approximation. If P is not too far away from Pi sat, over moderate changes, the liquid can be considered fairly incompressible. The volume will be more or less constant. It can come out of the integral, and that equation reduces to this form. So what this equation allows me to do is to calculate the fugacity of a liquid from known information and the fugacity coefficient of vapor at saturation condition. So if I can calculate fugacity of vapor at the saturation condition, I can use this equation and calculate the fugacity of liquid at an elevated pressure P. This term, exponential term in here, is known as pointing. So we have used the vapor liquid equilibrium concept to come up with an alternate way to calculate fugacity of species, of pure species in the liquid phase. We'll come back and try to work on one example using the pointing factor to correct the fugacity of liquid in the next lecture. Thank you.